Now it is your turn to write some code. In these labs you build and stress this chapter's operations. In C there is one rule for every program. You must free what you allocate, and when you have a ring, you must break the ring first before you free it. In Lab 1, you build the full core set of a doubly linked list. These are the 6 functions to write. Insert front adds a new node at the start. Insert end adds a new node at the end, and it is big O of 1 because you keep a tail pointer. Delete node removes a node you already hold. Print forward walks from head to tail. Print backward walks from tail back to head. And free returns every node to memory. Notice that head and tail are both passed by address as node double star, so each operation can update either one. One tip: because head and tail come in by address, every operation can fix either call or handle, and you finish with free, so each malloc meets exactly one free. To test your code, build the list 10, 20, 30, 40. Print it forward and backward. Then delete an inside node, the head and the tail, printing after each step. Now let's look at the Lab 1 solution. This is insert front, the first half. We call malloc for a new node and store its address in X. If malloc returns null, we return at once, so the list is left unchanged. We set X arrow data to K, then the new nodes on 2 links. X arrow prev is null because it will be first, and X arrow next is the old head. Here is the second half of insert front. If head is not null, the list already had a first node, so we set that node's prev to X, else the list was empty, and then X is the tail as well, so we set tail to X. Last of all, we set head to X. Moving head is always the final write. This is insert end, and it mirrors insert front. We malloc a node into X and return unchanged if that fails. We set X arrow data to cave in the new nodes on 2 links. X arrow next is null because it will be last, and X arrow prev is the old tail. Here is the second half of insert end. If tail is not null, the list already had a last node, so we set that node's next to X, else the list was empty, and then X is the head as well. So we set head to X. Last of all, we set tail to X. This is delete node, the first half. We guard first. If X is null, there is nothing to delete, so we return. Then we look behind X. If X arrow prev is not null, we set X arrow prev arrow next to X arrow next. So the node before skips over X, else X was the head, so we move head forward to X arrow next instead. And here is the mirror half. If X arrow next is not null, we set X arrow next arrow prev to X arrow prev, so the node after skips back over X, else X was the tail, so we move tail back to X arrow prev instead. Both neighbors now skip X, and only then do we free it. The full program with the 2 print functions, the free function and a test main, is in dlist_ops.c. Lab 2 is a tracing drill. You delete a node given only its pointer in big O of 1, and you name every pointer field the delete touches. No vague words like it relinks. Build the list 10, 20, 30, 40. Take a pointer to node 20 with no search. Before you write any pointer, print a line for each write. The line says which field you change, its old value and its new value. Then do the delete. A quick tip: there are at most 2 relink writes. One is X arrow prev arrow next. The other is X arrow next arrow prev, or head and tail in their place at the ends, plus the free. If you trace prints more than 2 relink lines, you touched a pointer you did not need to touch. Now the Lab 2 solution. This is delete traced, the first half. Notice the very first line. It saves the victim's data into a local variable before anything is freed. That way we can still print the value later without reading freed memory. Then, if the node has a prev, we print the first relink line and set prev arrow next to skip over the node. Otherwise X was the head, so head moves forward instead. Here is the mirror half. If the node has a next, we print the second relink line and set next arrow prev to skip back over the node. Otherwise X was the tail, so tail moves back instead. Both neighbors now skip the node, and only then do we free it. Now let's read the writes it makes, one row at a time. Write 1. Node 10's next field goes from 20 to 30. That is prev of 10, it's next. Write 2. Node 30's prev field goes from 20 to 10. That is next of 30, it's prev. Then we free node 20. The list is now 10, 30, 40. So an inside node takes exactly 2 relink writes, no more. This matches the prediction from the memory section. The full program is in lab_delete_trace.c. Lab 3 is the challenge. You simulate round-robin scheduling. That is how a CPU shares time between processes, one small slice each, again and again. You build a circular doubly linked list from only a tail pointer, and you write 4 functions. Ring insert end splices a new process in before the head. Ring print once walks 1 lap around the ring, using a do while loop. Round robin steps forward a fixed number of times, and ring free returns every node. Build a ring of 4 processes. Run round robin for more steps than there are processes, and watch the schedule wrap back to the first one. One tip, and it matters a lot. Ring free must break the ring first. You set tail arrow next to null before you free anything. If you skip this and just walk until null, the loop never ends because in a ring next never becomes null. So cut the ring, then free in a straight line. Now the Lab 3 solution. This is ring insert end, the first half. We malloc a node into X, and if that fails, we return the tail we were given, so the ring is unchanged. We set X arrow data to K, then comes the base case. If tail is null, the ring is empty, so X is the only node. It points at itself both ways, X arrow next to X and X arrow prev to X, and we return it as the new tail. Here is the second half for a ring that already has nodes. We read head, which is tail arrow next, then 4 writes in order. Write 1, X arrow next becomes head. Write 2, X arrow prev becomes tail. Those set the new node's own links first. Write 3, tail arrow next becomes X. Write 4, head arrow prev becomes X. Then we return X as the new tail. Now look at ring free. If tail is null, the ring is empty, so we return. Otherwise, we read head, and then we cut the wraparound edge once by setting tail arrow next to null. After that single cut, the ring is a straight line, so the ordinary walk works. Keep the next pointer in a local variable, free the node, and move on until we reach null. Cut the edge first, or the walk never reaches null and spins forever. Now let's trace round robin, 6 quanta over a ring of 4 processes. Quantum 1 runs P1. Quantum 2 runs P2. Quantum 3 runs P3. Quantum 4 runs P4. That is 1 full lap of the ring. Quantum 5 wraps back and runs P1 a second time. Quantum 6 runs P2 a second time. So 6 quanta over 4 processes wrap once. Remember, this is a simplified round-robin model, not a real kernel scheduler's data structure, but it shows the ring wrapping cleanly, with no end-of-list case. The full program is in circular_ops.c,